Ever wonder why your makeup mirror shows a massive close-up of your eye, while your car's side mirror manages to fit 3 entire lanes of traffic into a piece of glass the size of your hand? It comes down to the paths light takes when it hits a curved surface. This diagram shows a spherical mirror, essentially a slice of a hollow sphere. The horizontal line running straight through the middle is the principal axis. The exact center of the mirror surface is the pole, P. The center of that original hollow sphere is the center of curvature, C. And exactly halfway between P and C is the focus, F. To figure out how any mirror will reflect an image, you only need 2 rules. Rule 1, any light ray traveling parallel to the principal axis will hit the mirror and reflect diagonally straight through the focus. Rule 2, any light ray passing exactly through the center of curvature hits the mirror and bounces straight back along its exact same path. By tracking just these 2 predictable intersecting light paths, we can pinpoint exactly where and how any reflected image will form. Let's look at this concave mirror setup. If an object is infinitely far away, its incoming light rays run parallel. They hit the glass and converge exactly at the focus. As our checklist shows, this creates an image that is point-sized, real, and inverted. Move the object closer, sitting just beyond C, and our 2 golden rules kick in. The parallel ray goes through F, and the center ray bounces back. They intersect between C and F, creating an image that is still real and inverted, but diminished, smaller than the original object. Move the object directly onto C, and the intersection shifts again. The rays now cross directly below the object. The resulting image remains real and inverted, but now it is exactly the same size as the object itself. Notice the mechanical pattern. As the physical object takes a step forward toward the mirror, the reflected image takes a step backward and grows larger. Knowing that pattern, what happens if we move the object 1 step closer, placing it right between C and F? Pause the video for a second and try tracing the 2 light paths yourself. Here is the solution. Following the rules, the parallel ray and the center ray reach far out to the left. They intersect beyond C, forming an image that is still inverted, but now highly magnified. Now we hit a breaking point. Place the object exactly on F. The reflected rays run completely parallel to one another. Because they never intersect, the image is pushed out to infinity. If we step past F, moving the object right up to the mirror, the pattern shatters. The reflected rays don't cross. Instead, they physically spread apart in front of the mirror. To find the image, we have to trace those spreading rays backward. They appear to intersect behind the mirror itself. Our checklist updates. The image is now virtual, upright, and magnified. Crossing the focal point shifts the physics. Instead of projecting a real image into our physical space, the mirror now projects a virtual illusion inside the glass. Let's flip the curve outward to look at a convex mirror. Because the surface curves away from the object, the focus and center of curvature are actually located behind the mirror. If an object is infinitely far away, its parallel incoming rays hit the glass and bounce sharply outward. But human eyes trace lines straight back. We perceive those scattered rays converging exactly at the virtual focus point behind the glass. Move the object to any physical distance. The parallel and center rays bounce outward, but tracing them back forces an intersection between the pole and the focus. The result is always a tiny, upright arrow behind the mirror. Because the outward curve always scatters light, a physical intersection in front of the glass never happens. You get a wider field of view, but the image is permanently locked as a miniature virtual projection. Looking at this summary table, you can see how predictable these systems are. Out of 8 total scenarios across both mirror types, 6 produce real inverted images, and only 2 produce virtual ones. For exams, you can boil this entire chart down to 3 hard and fast rules. First, if you're using a concave mirror and the object sits anywhere outside the focus, your image is guaranteed to be real and inverted. Second, if that object crosses inside the focus on a concave mirror, the image switches completely. It is always virtual, upright, and magnified. Third, convex mirrors are entirely foolproof. No matter where you place the object, the image will always be virtual, upright, and small. By internalizing these 3 specific conditions, you have a built-in way to instantly verify your math and guarantee the accuracy of your ray diagrams before turning in your paper.